Welcome to This Explainer. Today, we're going to demystify the invisible infrastructure that makes modern global communication actually work. Right now, as we speak, we are surrounded by this intricate, totally silent system bouncing massive amounts of data back and forth from space, literally every single second. It's a system we completely rely on for our modern way of life, yet we almost never think about it.
To understand why this crazy space infrastructure even exists in the first place, we have to start with a fundamental physics problem. You see, the radio waves we use for telecommunications basically travel in a straight line. Engineers call this line-of-sight propagation. But the Earth, as we know, is a sphere. It's curved. So if you try to send a radio signal far enough across the globe, it's just going to shoot straight off the horizon and out into the void. So how on earth does a message actually cross the globe in seconds? Well, the brilliant solution was to basically put a giant mirror in the sky. By placing satellites high up in orbit, we can relay these signals around the curve of the planet, instantly connecting points that are thousands of miles apart.
So here is our roadmap for today. 1. The invisible space web. 2. Space and ground segments. 3. The orbital highways. 4. Finding the right frequency. And finally, 5. Connecting the world. Okay, let's jump right into Section 1, the invisible space web, a brief history of satellite communications. It is honestly incredible how fast this technology evolved. It all started out as just a concept in October 1945, when science fiction author Arthur C. Clarke published an article proposing what he called extraterrestrial relays in geostationary orbits. Just 12 years after that, in 1957, the Soviet Union launched Sputnik 1, and boom, the space age began. Now, Sputnik wasn't sending messages from point A to point B. It was mostly transmitting radio pulses to study the ionosphere. But it proved it could be done. Then, in 1960, NASA launched Echo 1. And what's super fun about Echo 1 is that it wasn't some highly complex computer system. It was literally a giant aluminized space balloon. It acted as a massive, shiny mirror in the sky, just bouncing microwave signals from one point on Earth to another. And that giant balloon brilliantly illustrates a massive leap in engineering that had to happen, the shift from passive to active satellites. You see, passive satellites like Echo 1 only reflect a signal. By the time that signal travels all the way up to space and bounces all the way back down, it loses a massive amount of power, what engineers call free space path loss. The signal becomes incredibly weak. Active satellites completely change the game. They actually receive the signal, amplify it, and then retransmit it back to Earth. The very first purpose-built active communication satellite was Project SCORE back in 1958. It actually carried a little tape recorder to broadcast a Christmas greeting to the world from U.S. President Dwight D. Eisenhower. Moving on to Section 2, space and ground segments, the two halves of communication. It really helps to think of satellite communications as two separate but totally cooperating segments. Up top, you have the space segment. This is the actual satellite floating around in orbit, packed with its payload of antennas, amplifiers, transponders, and of course, its power systems. Down below is the ground segment. This includes literally everything on Earth that talks to the satellite. We're talking massive dish antennas, modems, tracking software, and the human operators running the networks. Basically, the space segment generates and relays the data, while the ground segment tracks the satellite, catches the data, and decodes it. So to really get this, we need to understand the basic vocabulary of how these two halves actually talk. Whenever a ground station on Earth sends commands or data up into space, that's called an uplink. Up to space, uplink. Pretty straightforward, right? Conversely, when the satellite transmits payload data or telemetry back down to our stations on Earth, that is the downlink. Together, these two links are what keep the whole mission alive and the data flowing. So let's walk through the basic signal chain of how this actually happens. Step 1. Data is generated. Maybe it's a TV broadcast, or maybe it's just a command to adjust the satellite's solar panels. Step 2. That digital data goes into a modem. The modem uses modulation and coding to convert all those ones and zeros into a physical radio waveform. Step 3. The RF, or radio frequency chain, conditions that signal. It adjusts the power and makes absolutely sure it fits into the exact right frequency band. And finally, Step 4. The antenna focuses that energy and blasts it out toward the receiver. On the other end of the link, whether you're up in space or back on Earth, this exact same process is simply run in reverse to decode the message. All right, Section 3. The orbital highways, LEO, MEO, and GEO. It's important to realize that not all satellites live in the same neighborhood. We can think of orbits as different space highways. We start closest to Earth in LEO, or low Earth orbit. LEO satellites are only about 160 to 2,000 kilometers up. They are moving incredibly fast, zipping entirely around the Earth in just about 90 minutes. Because they're so close, the signal delay, or latency, is super low. That makes LEO absolutely perfect for modern high-speed satellite internet and IoT devices. But because they move so fast across the sky, you need a massive constellation of hundreds or even thousands of them to ensure you have continuous coverage. Next, we slow things down a bit and move higher into MEO, or medium Earth orbit. These sit between 2,000 and 36,000 kilometers up, taking anywhere from 2 to 8 hours to orbit the Earth. A MEO satellite has a much wider footprint, meaning you need way fewer of them to build a network. This is kind of the majestic middle ground, often used for GPS and really robust broadband services. And finally, we reach the highest highway, GEO, or geostationary orbit. GEO sits exactly 22,236 miles, or 35,785 kilometers, above the Earth's equator. I really want to emphasize just how incredibly far away that is. It is roughly 1/10 of the way to the moon. At this precise, majestic altitude, a satellite's orbital period exactly matches the Earth's 24-hour rotation. So to an observer on the ground, a geosatellite appears to stand completely still in the sky. It doesn't move. This is a game changer because it means you can bolt a satellite dish to your roof, point it at that one fixed spot in the sky, and literally never have to move it again. Which brings us to Section 4, finding the right frequency, the languages of satellites. Communication satellites operate across various frequency bands in the electromagnetic spectrum, and choosing the right one, well, that is a huge engineering trade-off. The lower frequency bands, like L-band and C-band, have lower data capacities, but they are incredibly reliable and essentially weatherproof. L-band, for instance, is heavily used for GPS and marine communications. As we move up into X-band, we see heavy government and military usage. But when we get to the higher frequencies, like Ku-band and Ka-band, the bandwidth capacity absolutely explodes. These are the bands that power our high-definition direct-to-home TV and provide the massive data throughput needed for modern internet constellations. But that massive capacity comes with a really severe vulnerability. Higher frequencies are highly susceptible to atmospheric interference. The biggest culprit is something called rain fade. Get this, the actual physical size of a rain droplet in the atmosphere is just the right size to absorb higher frequency signals like the K-band. It literally blocks the signal. Furthermore, the further a signal travels, the more it suffers from that free space path loss we mentioned earlier, where the power simply decreases over distance. Plus, certain frequencies are naturally absorbed by atmospheric oxygen and water vapor. So engineers are constantly performing this critical balancing act. Do you want a massive pipe of data that might cut out during a bad thunderstorm, or a smaller, highly reliable stream that will keep working straight through a hurricane? Let's wrap things up with Section 5, Connecting the World, Everyday Applications and Risks. You actually interact with this invisible web all the time. If you have direct-to-home TV, you're likely pulling down Ku-band signals from a satellite, sitting totally motionless 22,000 miles above the equator. If an explorer or, say, a ship captain is out in the middle of the Pacific Ocean, they are relying on remote satellite telephony via LEO or MEO networks like Iridium or Inmarsat just to make a lifeline call. And today, high-speed LEO megaconstellations like Starlink are blanketing the globe to provide internet access to regions where laying fiber optic cable is just physically impossible. But we do need to look at the darker side, the hidden vulnerabilities of this massive system. The inherent openness of wireless transmission totally exposes our data. Many older satellite systems use unencrypted or very weakly encrypted protocols. For example, the DVB-S protocol used for a lot of broadcasts is often just completely unencrypted. And because a satellite sitting high in orbit has a massive geographic footprint, literally anyone within thousands of miles who happens to have the right antenna can intercept that downlink. Furthermore, that incredible distance to geostationary satellites creates high latency, a delay in the signal. That delay can actually be exploited by hackers for man-in-the-middle attacks. And because bandwidth is so incredibly precious and expensive up in space, operators will sometimes actually sacrifice security, disabling heavy encryption protocols just to reduce their overhead and squeeze a little more data through the pipe. All of this leaves us with a pretty profound question. We have built an incredible, invisible web of orbital highways, beaming massive amounts of data back and forth to connect humanity in ways Arthur C. Clarke could only dream about back in 1945. But with unencrypted protocols, wide-open signal footprints, and atmospheric vulnerabilities, just how secure is this vital infrastructure bouncing 22,000 miles above our heads? It is definitely something to think about the next time you connect to the world from the middle of nowhere. Thanks so much for joining me on this explainer, and I'll catch you on the next one.